Take a look at this simple piece of code. What do you think happens here? I suspect many people imagine this sequence. First, inside the make string function, a temporary string object is created from hello world. Second, when the function executes return, this temporary object is thrown out as the return value. Third, in the main function, the copy or move constructor is called to copy or transfer the contents of the temporary object to the result variable. Fourth, the temporary object's lifetime ends. It is automatically destroyed and memory is released. Many might even go into detail. First, allocate stack memory for the temporary object. Call the string constructor, copy the string data, trigger a move upon return, then destruct the temporary object, a seamless sequence that they believe is how C++ executes. But I'm telling you, none of the steps above actually happen. There's no temporary object, no copy, no move. Even the return value object you imagine never actually exists in memory. Many may be puzzled as to why. Before diving into the core principle, let's first clarify 5 fundamental concepts so you don't get lost later. First, a temporary object, also called a prvalue, is an object without a name. For example, when the code says return hello, the compiler implicitly generates a string object without a variable name. It exists only within the current expression and has an extremely short lifetime. You usually can't see or touch it. You have to imagine it. Second, the copy constructor creates a new object that is an exact copy of an existing object. It duplicates all the data of the object. For a type like string that manages heap memory, copying also requires allocating new memory, making it less efficient. Third, the move constructor introduced in C++11 steals the resources of a temporary object and gives them to the new object. It doesn't copy data. It only transfers ownership. It's faster than copying, but it still essentially creates a new object and transfers resources. Fourth, RVO stands for return value optimization. It applies when a function returns an anonymous temporary object directly. Fifth, NRVO stands for named return value optimization. It applies when a function returns a named local variable defined inside it, which is the most common pattern in everyday development. Many people understand C++ in terms of code executing line by line, but the C++ standard only defines the behavior of the abstract machine. The compiler only needs to ensure that the final outcome matches the abstract machine. The intermediate steps can be freely rewritten. The abstract machine doesn't care how many constructors you wrote or how many steps the return took. It only requires that the final variable holds the correct value. The standard doesn't require whether there were temporary objects or copies in between. This is precisely why the compiler dares to skip intermediate steps. As long as the result is correct, the process can be entirely reconstructed. With these basics in mind, let's step beyond the language level and look at the underlying function calling conventions. This is the hardware level foundation that makes RVO possible. The conventional function call stack logic that many imagine goes like this. Main sets up a stack frame, then calls make. Make creates a temporary string in its own stack frame and copies that temporary to a return value buffer. Main then copies the data from the buffer into the variable ses. Finally, make stack frame is destroyed and the temporary object is destructed. This sequence requires 2 memory copies and takes up extra stack space, the intuitive execution flow most people assume. But the actual stack logic when copy elision is enabled is completely different. Main allocates stack memory for the target variable s directly when setting up its stack frame and passes the memory address of s to make as an implicit parameter. Make then constructs the object directly at the memory address provided by main without creating any temporary object in its own stack frame. When the function returns, it simply cleans up its own stack frame. No extra memory copies are performed. In short, the caller pre-allocates the target memory and the callee constructs the object directly in that memory. The entire process has 0 copies, 0 temporaries, and 0 data movement. That's the underlying implementation of RVO. There's no black magic here. The compiler simply changes where the object is constructed from construct in the child stack frame and copy to the parent to construct directly in the parent stack frame. Now that we understand the underlying principle, let's look at how the C++ standard has evolved. This is the key to distinguishing between optimization and mandatory rule. In C++ 9803, RVO was an optional compiler optimization. The compiler could apply it or not without violating the standard. It was entirely up to the compiler. In C++ 1114, move semantics were introduced. Even if RVO didn't apply, move constructors could reduce overhead, but temporary objects could still exist, and the optimization remained optional. By C++ 17 and later, the standard introduced mandatory copy elision, writing it directly into the language rules. For RVO involving anonymous returns, the compiler must perform it. There's no room for negotiation. For NRVO, named return, it hasn't been made mandatory by the standard, but modern mainstream compilers aggressively optimize it by default. So in day-to-day development, you don't need to worry about copies or moves being triggered. So you must understand, since C++17, this is no longer a matter of the compiler's kindness in optimizing. It's a rule of how the C++ language itself executes. Even if we manually disable all compiler optimizations, the compiler is still required to execute by constructing the object directly at the target location. No temporary object will be generated, and no copy or move constructor will be called. If we compile with GCC, disable all optimizations, and specify the C++17 standard, we can clearly see in the generated assembly, there's only one call to string structor with the address pointing directly to a variable in main stack frame. No copy constructor, no move constructor, no stack space allocated for a temporary object, and no memory copy instructions. This conclusively proves that copy elision in C++17 and later is a standard requirement, not an optional optimization. Let's look at some verification code to confirm this conclusion. We'll delete both the copy constructor and the move constructor of a class, making it neither copyable nor movable. According to conventional logic, objects of such a class shouldn't be able to be returned from a function. The compilation should fail. But when we compile with the C++17 standard, the console only prints two lines, test object constructed and test object destructed. Only one constructor and one destructor are called, no trace of copy or move. The code runs perfectly without any error. If we followed the mistaken mental model earlier, this code, being unable to copy or move, shouldn't be able to return an object at all. Yet it runs fine. The only explanation is that there's no actual value return process happening, no temporary object. The object is constructed directly at the location of the object variable in main. You can verify this yourself. Use G++, disable all optimizations, specify the C++17 standard, and see the result with your own eyes. Of course, not every return scenario can trigger this optimization. There are two common edge cases where it may not apply, which are good to know. One is returning a parameter passed into the function. For example, if the function receives a test parameter and simply returns that parameter, NRVO won't apply because the memory address of the parameter isn't within the stack frame that the compiler can control for this optimization. Another is returning named objects from multiple branches. This is an edge case. For instance, if the function has several if branches and each returns a different local variable, some older compilers might not apply NRVO. Even modern compilers can't guarantee optimization in 100% of cases, so in very rare scenarios, a move may still be triggered. But rest assured, in 99% of everyday cases where you return a local object, the optimization will be applied reliably. You can write such code with confidence. Now that we've covered the principles and verification, let's correct 3 common misconceptions to avoid developing biases. First, returning an object first creates a temporary object and then optimizes away the copy. Since C++17, when returning an anonymous temporary, no temporary object is created at all. The copy is not optimized away. It simply never existed. Second, move constructors are faster than RVO. Move constructors still require creating a temporary object and transferring resources. RVO skips all intermediate steps entirely, incurring 0 extra overhead. It's much faster than move. In practice, RVO is always prioritized over move. Third, if I disable compiler optimizations, RVO stops working. After C++17, RVO is a mandatory part of the standard and must be performed even with optimizations disabled. This only applies to pre-C++11 standards, where disabling optimizations could indeed prevent RVO. Finally, here's a practical question for you. If we return a unique _PTR, an exclusive smart pointer that cannot be copied, only moved, can RVO still apply? What's the difference in execution compared to ordinary objects? If you know the answer, feel free to share it in the comments. See you in the next video.